In Chapter 5, we are going to be using trig identities to rewrite expressions, to verify relationships between trig functions or functions involving trig functions, and to solve problems, okay? So we've already seen some trig identities. We know the fundamental identities, which is the reciprocal identities here. We also know these two quotient identities about tangent and cotangent. All of the other ones we are going to be learning. We're going to start with these two in 5.1. These are not formulas where you will have to have all of them memorized. You will get this sheet like on assessments, quizzes and tests and such, but we do need to be pretty familiar with them. Okay, so let's look at 5.1. 5.1, we are starting with what are called the Pythagorean identities. Now, before we get to those, let me try and move this here. Remember from our unit circle, any point with coordinates x, y that is on the unit circle can be written as the cosine of the reference angle, comma, sine of the angle, okay? Or I guess technically not the reference angle, but the central angle, okay? In other words, if I have a point that's on, let's see, here's part of my unit circle. Let's say I have a point right here, okay? I can turn that into a right triangle, and this x, the radius is always 1 for a unit circle. This distance here is the x coordinate of this point, and this distance here is the y coordinate of that point, okay? So then, because of SOHCAHTOA, we know that the opposite over hypotenuse, so y over 1, would be the sine of the angle, so this is sine of theta, and that x over 1 is the cosine ratio for theta, so x is equal to, the x coordinate is cosine of that angle. Okay, why do we care about that here? Well, we also, when we have a right angle, have a Pythagorean theorem relationship where x squared plus y squared is equal to 1. Or in either order, I could do y squared plus x squared. Doesn't really matter. Addition is commutative, okay? But from that, replacing our x and y with cosine and sine, we get the first of our Pythagorean identities. So sine of theta is the same as y. So this is the same as writing y squared. Cosine of theta is the same as x, so that this is the same as writing x squared, and then 1 squared is just 1, okay? So this Pythagorean identity comes from somewhere. It comes from the fact that we have a right triangle in the unit circle, and we can replace our x and y coordinates, the two legs of the triangle, with sine theta and cosine theta, and then the hypotenuse is 1. So this is our a squared plus b squared equals c squared Pythagorean relationship, but written with trig functions. Okay, now, from this first Pythagorean identity, we can get to the other two. So if I want to write an identity that has tangent in it, well, I know that I have a sine expression here, and if I divide that by cosine, then I'll have tangent, because sine over cosine is tangent. And by the way, when we talk about these, we say sine, cosine, tangent. We don't usually say of theta, but just be careful that when you are writing it, you are including the theta, because I can't, like, sine squared does not exist by itself. It has to be of something, okay? So even though we say sine, make sure that you are including notation for whatever the angle is, theta or number or x or whatever. Okay, so to get to tangent, I'm going to divide this by cosine, but algebra says if I divide one piece, I have to divide the entire thing. So I'm actually going to divide both sides of the equation by cosine squared theta. Sine squared over cosine squared gives me tangent squared. Cosine squared divided by cosine squared is 1, because those cancel, and then 1 divided by cosine squared we know to be secant squared, okay, which is the second of the identities. So these are not, these are not just made up independent from each other, but there's a relationship between the first one and each of the other two, okay? Now let's say that I'm starting with my original one again. I'm going to rewrite it over here. Sine squared theta plus cosine squared theta equals 1. But now I want an expression or an equation, an identity that involves cotangent instead of tangent. Well, cotangent is cosine over sine. So now, seeing that I have a cosine squared here, I know that if I divide that, and therefore the whole equation, by sine squared theta, that is going to give me a cotangent in the middle. Sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared, and 1 divided by sine squared is cosecant squared, which is how we get this identity right here, okay? So those are the 3 Pythagorean identities. We start with sine squared plus cosine squared equals 1, and then we either divide by cosine squared on the entire equation, or we divide by sine squared in the entire equation to get to one of the other 2, okay? So we do need to be familiar with these, but not only in this form. We need to recognize them if they are rearranged at all as well. So for example, instead of seeing sine squared plus cosine squared and then knowing that we can replace that with a 1 because they're equivalent, maybe we see something like 1 minus cosine squared, okay? And then as part of our problem, we need to recognize that this is equal to sine squared, because if I take this and I subtract my cosine squared from both sides, I would have 1 minus cosine squared is equal to sine squared, okay? Or maybe on this one right here, I end up having a negative cotangent squared of theta plus cosecant squared of theta, okay? And I want to know what is that equal to in the context of some other problem. Well, negative cotangent means I've got that on the other side, so essentially I've subtracted this from both sides. Positive cosecant squared, that's going to be equal to what's left on the other side of the equation is going to be equal to 1. Okay, so I'm not going to give you these 3 identities in every possible form you might see, but you need to recognize that if you see an expression that involves maybe a 1 and a secant squared, there's probably a relationship with tangent squared somewhere. Or if you see something that involves cosecant squared and a negative 1, there's probably an expression that can be replaced with cotangent squared. And if you need to write this out and then actually, physically say, okay, well, what happens if I subtract cotangent squared from both sides? Now, do I have something that matches the expression that I'm given? Yes. What's left? A 1. That's fine. Okay, so those are the Pythagorean identities, and we are going to be using those. Additionally, we are going to be using some symmetry identities, okay? If you think back to somewhere in algebra, you would have seen functions that have symmetry, meaning they are either even or odd functions. It's very likely that you were shown graphs of functions and you were asked to identify whether those graphs were even or odd functions. And an even function, if you remember, is a function that can be reflected over the y-axis. In other words, I can fold it in half and it lands on itself. So a good example of that would be something like the absolute value of x. Okay, this is what the absolute value of x looks like. If I fold this on the y-axis, one side will land on the other side, so it is an even function. An odd function is one that has rotational symmetry around the origin, meaning I can take my function, rotate it 180 degrees, and it lands on top of itself. So, for example, the cube root of x is something that looks like this, okay? And if you didn't have that memorized, no big deal. But if I take the cube root of x and I spin the graph around the origin 180 degrees, this piece right here lands on top of this, and this one lands on top of the other, okay? So that is an odd function because it has rotational symmetry around the origin. Okay, so how does that apply to trig functions? Well, when we write even and odd functions algebraically, we actually define them by evaluating the opposite of x. So let me write down what I mean. If a function is even, then it has to be true that f of negative x is equal to f of x. Okay, in other words, if I plug in the opposite input for any value, I get the same thing out. Or think of it this way, if I plug in a number that is to the left of, let's say a number like right here, if I plug in a number that is to the left of the x-axis, I should get the same output as if I plug in that same distance to the right. And I do on an even function, okay? So if f of negative x is equal to f of x, I have an even function, all right? And if we look down below at these 6 graphs, we can see that, and now these don't have transformations involved. Like if I have a phase shift, then this does not apply. But on the basic functions, okay, on these graphs, I see that cosine and secant are both graphs that are even. I could fold them on the y-axis and they would land on top of each other, okay? So these two right here are both even functions, all right? Now, we're not going to be graphing in this section, but what we might do is if we have an expression for cosine of negative, let's say cosine of negative 5 pi over 6, we know that that would be the same as cosine of positive 5 pi over 6 based on this even identity, okay? Then for an odd function, remember those are the rotationally symmetric ones, we define it as f of negative x is equal to the opposite of f of x. Okay, so in other words, if I plug in a value to the left and right of 0 by the same amount, I should get opposite results. So if I plug in a number over here, I get a height here. If I plug in that same number on the other side, I should get the opposite. So these two vertical distances should be the same, which makes sense if we have rotational symmetry. Okay, so sine and cosecant, these are graphs. If you imagine spinning this 180 degrees around the origin, it would land right here, and vice versa. Same thing with cosecant. This asymptote stays where it is. This asymptote and this asymptote switch places. This one spins around over here. This one spins over here. And then same thing with the u's. This one right here flips over and becomes this. This one right here flips over, becomes this. So sine and cosecant are odd functions. Okay. Likewise, tangent and cotangent are odd functions. It's really obvious when we look at the tangent graph because it looks almost kind of like the propeller looking thing that I have for the cube root, just, turned upright. So if I take this piece right here, rotate 180 degrees, it lands here. If I take this right here, rotate 180 degrees, it looks like that. Okay, so both of these are odd. Kind of ran out of room on the right there. Both of these are odd functions as well. Okay, again, we're not going to be looking at the graphs of them. Okay, I wanted you to be able to visualize that with the symmetry, but we will be rewriting using these identities. Okay. All right, so let's do a few examples here. All of these are using identities either up above or the ones that we already know, like the reciprocal identities. So this says if sine x is equal to 4.61, then what is sine of negative x? Well, according to what we just talked about, sine is an odd function, meaning sine of negative x is the same as, I'm going to add a step in between here, is the same as the opposite of sine of x. And what does sine x equal? Well, we're given in the problem that sine x is 4.61, so sine of the opposite of x is negative 4.61. And that's all we need to do right there. Okay. For number 2, it says secant of x is equal to negative 3.1, and we're looking for cosine of x. Well, we know the relationship between secant and cosecant is that they are reciprocals of each other. So if I know that secant of x is negative 3.1, cosine is the cosine ratio for x. Okay, we're not changing the angle, we're changing the ratio. Turn it into a fraction if you need to. The cosine of that same angle is the reciprocal of this. So negative 1 over 3.1. Or you can put the negative in the bottom, it's the same thing. Okay? And then for this last one, it says if tangent of theta is 3/5, then what is the opposite of tangent of negative theta? I'm going to do this one in a couple of steps. Tangent of negative theta is, according to this identity, because tangent is odd, it's equal to the opposite of tangent of theta. So inside the parentheses here, tangent of negative theta is equal to the opposite of tangent theta. And now I have negative times negative, that's just positive tangent theta. So negative, or the opposite of tangent of negative theta is the same as tangent of the original theta, so 3/5.